Welcome to the e-Pathshala lecture series on computer science for postgraduate students, and this is the 18th module of computer graphics and visualization subject. Okay, so we have learnt in the previous module how visible surface detection methods are actually used, and why do we need to remove a surface that is behind, or a back face, or we call it a back face. So why don't we consider faces that are visible and only take them from a given viewing position or given a viewing position. So in this module, let us focus on the other important aspect of computer graphics, which is color models. So which is an important thing as far as for you to understand how colors are reproduced on a system and how colors are used, and the theory behind them. So let us see what are the objectives of this module. So to understand what is color and how it is represented in graphics applications. So what are the various color modes and color models? We call them modes. We can also call them as color mode or model, whatever. The popular color models are RGB, CMY, YIQ, HSV and HLS color models. Okay. So let us understand what color is, or how do we represent color. So how do we model color and how do we use color, and in what context we use color and how do we use them. So color is nothing but we can define that as it is made up of three attributes. One is like, say, the dominant wavelength or hue, the other thing is intensity or brightness, and the other thing is saturation. So we can understand that a color can be defined with the three parameters: the dominant wavelength. So wavelength of what? Here wavelength is what? Wavelength is nothing but the wavelength of the light that is reflected and that enters into the human eye. So imagine you are standing in an open area, and imagine it is a daylight. So what you see actually is not the light itself. What you see is actually is the light that gets reflected from the objects. So what we see is the light that falls on the object and gets reflected. So we see the reflected light. So here the word wavelength means the wavelength of the reflected light. Okay, the wavelength of the reflected light. So light, we can imagine that it is in the electromagnetic spectrum. We got from violet to red, the VIBGYOR. So there are wavelengths, and the wavelengths of each of these lights. So we can classify them into bands of wavelength bands, and accordingly we have got various colored lights and so on. So here color models are the interesting things that we will look at. So as you can see here, the color models, the light is an important thing that you should understand. So light in an electromagnetic spectrum is understood to have various frequencies and various wavelengths from violet to red and beyond. Okay. So which is the electromagnetic spectrum. So the color is fundamentally defined by the three parameters: the hue, which is called the dominant wavelength, very important, the dominant wavelength. Out of lot of light that gets reflected from objects, okay, light falls on them and light gets reflected. Out of lot of light that falls on them, only there is what we see is the dominant wavelength. Not all wavelengths we see the dominant wavelength. So whichever is dominant among all the other wavelengths. And the humans are also limited in their viewing range. We do not see all possible colors and we do not see all possible wavelengths, we see only specific wavelengths. The next important parameter is the saturation, which talks about the purity of the light. The third parameter is luminance, which gives the intensity or brightness of light. So the three important parameters that define light that define color are the hue, the purity or saturation, and intensity or brightness. The word chroma refers to color. So if we say chroma, means it is a combination of hue and saturation. Chroma defines color, while luma parameter, which is intensity or brightness of that color. So as we know, when we combine two colors we get white. So if those two colors are called as complementary colors. So red and cyan, green and magenta, and blue and yellow. So color models are used, or color models use three colors, two, sometimes two also. So 2 to 3 colors a minimum of, so to produce all possible colors. So as you can see, If you take RGB color model, if I say RGB is my color model, what do I mean to say is I have got an R, I have got a G, I have got a B, and I am going to combine them in various proportions to get the colors of my choice. So I take some R and G, as you can see in a color palette. So a combination of colors, if you can see, the monitors can produce 16 million colors. So 2 power 24, if 24 bits we assign to a color, the possibilities are 2 power 24. The other powerful monitors can still produce 2 power 32 possible colors are there. So why these are possible, we say is the amount of each of these colors that we combine to get a color of our choice is the color that we see. So these 2 or 3 solid colors that we are using and we are combining them. So these 2 or 3 are called the primary colors. So if we take the 2 or 3 colors which are used to produce many other colors are the primary colors. And what is color gamut? The color gamut is the range of colors that a color model can successfully produce. Color gamut for RGB might be different from color gamut from say cyan, magenta, yellow color model, the CMY color model. So color gamut for CMY may be different from the YIQ color model. Color gamut for YIQ color model may be different from the HSV and HLS color models and so on. Before we go to understand actually what is a color model and what is a color gamut, let us look at a theoretical color model. From that we will derive some concepts and we will apply that on the real color models or the practical color models. So let us understand some theoretical color model, a theoretical color model, say XYZ color model, where XYZ are the 3 primary colors which when combined produce many possible colors. Okay. So the amounts of, as you can see in the slide here, the amount of red, green and blue needed to produce any spectral color can be represented through what is called color matching functions. So what is a color matching function? Here as you can see on the graph, so there is a function for B, function for G, function for R. So each of them are curves. The x axis has got the wavelengths. Suppose for example you wanted to produce a color at exactly say 550, 500 and say for example 525 is the wavelength. There you want to produce a color at that wavelength. So what do you do is at 525 you can take a little of blue, as you can see from the curve, you can take a little of blue, you can take some good amount of green, and you have some amount of red which is on the negative side. So what do you do? As given in the equation there, for a color of our choice you can take some amount of red, blue, some amount of green and subtract the amount of red from it. Okay. The red curve alone has got some part of it in the negative direction, but otherwise leaving that part, if you go beyond say 550 and 600, if you want a color to produce at 600, what you do is simply add the amounts of green and red. You do not have to bother about blue. So that is how we can produce any color using the color matching function. So the CIE XYZ color model is a Commission International, it is an Italian, the expansion for it. So do not worry more about the expansion. So CIE color model, it says what is a theoretical color model and how do we understand what is the color gamut and many other concepts from theoretical color model. So we are calling it theoretical because we have RGB, CMY which are practical color models. So imagine there are 3 colors X, Y and Z and they are the primaries, and that means we are going to combine X, Y, Z in some proportion to get the colors of choice. The XYZ color model says that the 3 colors are to be added and any color C lambda is expressed as a proportion of A is the proportion of X, B is the proportion of Y and C is the proportion of Z. So the proportion of X is A and proportion of Y is B and proportion of that is C, and these amounts of these amounts A, B, C and A, B, C actually are to be determined as per the wavelength, the color choice that we want. So where ABC designates the amounts of standard primaries that are needed to match the color C lambda. What we are doing is, in fact theoretically we cannot say all the time that okay ABC are some proportions. Instead we can normalize the amounts so that we can use them, because always exact amounts are not possible because we use different different quantities of colors every time in different proportions we require. So, we generally take normalized amounts of the colors. So, given the actual amounts, how to get the normalized amounts is, say for example, let x dash represent the normalized amount of say A, let y dash represent the normalized amount of B, which is B by A plus B plus C, z dash represent the normalized amount of C, which is C by A plus B plus C. So these ratios are always either 0 or 1. So the minimum maximum is 0 and 1 for the normalized amounts. As the relation is now valid, x dash plus y dash plus z dash is always equal to 1 because of the normalization step. So now given two colors, can you produce the third color? Given two normalized amounts, say for example given x dashed and y dashed, we can compute easily z dashed because we have the relation. So x dashed plus y dashed is equal to 1 minus z dash. So if you can get z dashed, if you want 1 minus x dashed minus y dashed, you get z dashed. So given two normalized amounts, you can get the third normalized amount, but given the normalized amounts, can you get the actual amounts? Because always we need to find a mapping from normalized amounts to actual amounts, because you need to convert these numbers to the actual volumes you have with you, actual quantities of colors you have. So given normalized amount, how to get the actual amounts, which is not possible in fact. So if you are given x, y, z, x dashed, y dashed, z dashed, even if you are not, if you are given all the three, you will not be able to compute A, B, C for sure. Okay. So what do we do is we generally take two normalized amounts and one actual amount, so that we can compute the other two actual amounts. Okay. What is that we are doing? We are taking two normalized amounts and one actual amount. Okay. For example, if you take x dashed and y dashed, you can take one actual amount, say B also along with that, so that as can be mentioned there, say x dashed and y dashed and B are known, then you can easily compute A and C, okay, as shown there. So the color matching for the positive primaries, the imaginary primaries, the x, y, z primaries are all on the positive side. So x, y, z, as you can see, these are the color matching functions. The advantage of this color model, so as I said in the beginning, we are looking at this theoretical color model to understand some concepts, okay, of the color models. The theoretical color model is advantageous for what is called understanding color gamuts. So identifying complementary colors and identifying dominant colors and identifying saturation of a given color. So as can be seen here, if you draw a graph for the x, y, that is x dash to y dash, the two normalized amounts, as we took earlier in the two normalized amounts and one actual amount. If you draw a curve, it is a 2D graph, and the shape is called the tongue shape. So the shape that we see is the tongue shape, and on the boundary of the tongue shape we have the colors that are purest form. At the center we have got the white, which is indicated with the letter C, got the white there, and an imaginary line that is connecting the violet and the red, which is a dotted line, as you can see, which is not there. In fact, we are simply connecting it, okay, we are simply for closing the figure and for understanding purposes we have added, but that is not there actually in the graph. So the color gamut, what is now the color gamut? Color gamut is nothing but a range of colors that a color model can successfully produce. Now let us say a color model is nothing but made up of 2 or 3 primaries. As you can see from here, let C1, C2 be the color model, okay. C1 and C2 are 2 different colors. Now connect them with a straight line, 2 different colors in the diagram, connect them with a straight line, okay. And what happens if you combine these C1 and C2 in various proportions? And when you combine these two colors in various proportions, what you get are the colors and that exactly fall along the line connecting C1 and C2. What is that again? Let me repeat. So C1 and C2 color model, if we take, what do we understand by that is, if we combine C1 and C2 in various proportions, the colors we get exactly fall on the line connecting C1 and C2, okay, fall on the line connecting between C1 and C2. So we can say the color gamut for C1 and C2 are all the colors that fall along the line connecting the two colors C1 and C2. Similarly, take 3 colors C3, C4 and C5 which form a triangle like. So what is the color gamut for the color model C3, C4, C5 are all the colors that fall in the triangle inside the triangle that is formed by these 3 colors as 3 vertices. Okay, so it is called C3, C4, C5 color model. So that is how we understand. So what are complementary colors? Complementary colors are colors that when combined produce white. I mean, take any 2 colors and when you connect them with a straight line, if the straight line touches the if the straight line passes through the center white, C is the white color, white, it is touches the white, we say those 2 colors are complementary colors. So any 2 colors when combined, if they produce white, we call them complementary colors. And the purity of a color from the center to the boundary, say for example the purity increases. So the purity is maximum on the boundary. As you know, pure colors are on the boundary, and as you move towards the center there is no purity, it is white. So saturation is 0 at the center and saturation is full and 100% at the edge. So if you want to know the saturation of a given color, how pure it is, see how much far away it is from the boundary. Okay. So as can be seen, for a color C1 the saturation is given by C1 minus C by Cs minus C. Okay. So let us see the first and the foremost color model, the RGB color model, which is the most used color model, and the best example is your monitors. Your computer monitors or your display devices, most of them use RGB color model. They combine R, G and B in some proportions to get colors of choice. So the RGB color model, the 3-dimensional color model, we call it, is represented in a cubic form, in a standard unit cube form. Okay. So that means the cube has edges that are of size 1, it is a standard unit cube. The R axis, the G axis and the B axis. At the center, the origin is actually occupied by the B, the black, and the opposite, diagonally opposite vertex is for the white. Okay. The line connecting the black and white are all the grey. Okay. The colors that fall along the line connecting the black and white are the grey. All the other vertices are occupied by the what is called by the important colors. The red and green, when you combine, what you get is the yellow vertex. Green and say blue, when you combine, you get the cyan vertex. Blue and red, when you combine, you get the magenta vertex. So as you can see, the vertices are also represented there. Okay. The best example is the monitors and display devices. So the colors are added to get colors of choice. So that is why these are called additive primaries. Now what is the color gamut for the RGB color model, which is a practical color model? The color gamut is nothing but all colors that lie within the standard unit cube. Okay. Similarly, the color model CMY is also an important color model that is used in the print media. If you take printer, say monitors, and we have got RGB color model, they use them, and printers, if you take, they do not use RGB, they use instead the cyan, magenta and yellow inks to produce colors of choice. So now given you want say some red color, you have cyan, magenta, yellow inks in the printer, how do you produce some color of your choice? Again, as you know, it is called subtractive color mixing. Okay. Cyan absorbs red, as cyan and red are opposite, so cyan absorbs red. Blue is blue, that is magenta absorbs green because they are opposite colors. So blue and yellow, they are opposite colors. So what happens actually is the color model, the CMY, the cyan, magenta and yellow color model is also represented using the same standard unit cube, but the difference is that the cyan axis, the magenta axis and the yellow axis, at the origin we have got white. Earlier in the RGB color model, at the origin we have got black, now we have got white here, and on the opposite vertex we have got black here. So the grey line is the line connecting the diagonally opposite vertices, the white and the black. Okay. Now at the intermediate vertices we have got blue, red and green. That means if you combine cyan and yellow, you get green. If you combine cyan and magenta, you get blue. So but instead of adding here, these CMY use subtractive color mixing, where colors are subtracted, the primary colors, say the red, green and blue, are subtracted from the respective cyan, magenta and yellow, so that we get color of our choice. So, as you can see here, the color gamut for the cyan, magenta, yellow color model is slightly closer in size to the RGB color model. Okay. The CMY, if given RGB values, you can easily get CMY by subtracting the RGB values from 1 and vice versa. The next interesting color model is the YIQ color model. So, why do we have these many color models? What is the fun in having these many color models is that, as I said, it is not possible that we can use one color model and produce all possible colors in the world. That is the limitation of the color model. Okay. Not all colors in the world are possible in a color model. So, that is why, for example, if you want to produce human skin color, the best color model is the HSV color model. So, some colors are possible in a color model, and those colors may not be possible in a different color model, but the colors that are not possible in the first color model may be possible in the second color model, and so on. So, the color gamut for each of these color models is different. The next practical color model is the YIQ color model, or YUV it is also called. In literature it is also called as YCBCR. The Y stands for the luma component, the UV stand for the chroma component of the color model. Okay. The Y stand for the luma component, the I and Q or U and V or CBCR, as you can call, they form the chroma component. That means the chroma information is sent using 2 values and the luma information is sent in 1 value. Okay. The YIQ color model, where is it popular? Do you know where this is used? Or as it is in television broadcast, uses the YIQ color model or the YUV color model. Even the DVD players or the back side of these players, you can see that it supports the YUV format, it supports YCBCR format. So, this color model is such like where as what happens in a television broadcast is that at the base station, at the source station, what do is they combine Y, U and V on one as one value, as one single value, and they transmit this single value, and at the receiving end the values are separated into Y, U and V, and they are used by the television set or your DVD players or other display devices. So, that is why it is called composite color model. That means all the values are sent across one single cable, one single value. So, these are very useful color models which occupy less bandwidth. So, they are very much useful as they occupy less bandwidth. The next interesting color model is the HSV color model, which is the practical color model. Okay. You must observe one thing, each of these color models that we are talking about are represented using a shape or using a volume. RGB color model we used standard unit cube, YUV color model we used a standard unit cube. The HSV color model is represented as a volume, and the volume has the shape of a cone, a hexacone. We call it, it's a hexagonal cone we can call it, or called in short it is called as hex cone. Okay, it is a hexagonal shape on top and it is like a cone, so that the shape is hex cone. Now, how do we represent a color in this hex cone is say HSV we call it. So, a color is given with the 3 values, the H value, the S value and the V value, and the color gamut for HSV color model are all the colors that lie within this hex cone volume. Okay. H is hue, S is saturation, V is value. H is measured as an angle between 0 to 360, S is measured as a value between 0 and 1, and V is a value, that is intensity you can call it, between 0 to 1. Imagine a hexagonal cone. On top of the hexagonal cone, that is the top plane of the hexagonal cone, and on the boundary of the hexagonal cone there lie all pure colors. Okay, hexagon means there are 6 vertices starting with red, yellow, green, cyan, blue and magenta. At each of the vertex we got, and on the boundary we have got purest colors in the purest form, and the white is at the center and on the top plane, and the black is at the vertex of the hex cone. Okay. The line connecting the black and the white is the gray line. Okay, the colors that fall along the line connecting the black and white is the gray line. And how do you now find a color? So to find a color you need to give the 3 values, the H, S and V. Okay. Now what is HSV for red? I say H value is say 0 degrees, S is say 1 and V is say 1. Okay. So for all the pure colors on the top plane of the hexagonal cone, the V value is 1. So V is fixed. S value on the boundary of the hexagonal cone on the top plane is 1. And as we move towards white, we have, as we move towards white, the saturations saturation reduces to a value 0. So at the center of the what is called the volume, that is at the center at the white, S is 0. Okay. Now the axis that connects the black and white is the V axis, the value, we can call that as value axis. The hue is measured like an angle from 0 degrees. So R at 0, yellow at 60, at every 60 we have got a pure color, that is we have got pure colors on the boundary for sure, but the important colors, the red, green, blue and the cyan, magenta and yellow are at every 60 degrees. Okay. Now if you are to identify a color, you need to get all the H and S and V values corresponding. So adding a black pigment to a color produces shade of that color. We have the important terminology here: shades, tints and tones. A shade, we get a shade of a color when we add black pigment to the pure color. That means as we add black, we get a shade of that, and the shades lie on the boundary and towards the bottom. So they move towards the bottom. All the colors that lie on the outer surface of the hexagonal cone and on the boundary of the hexagonal cone, from the top plane to the vertex, all the shades. So when we add more and more black pigment, we get colors close to the vertex. Okay. So shades lie on the surface of the hexagonal cone, and tints lie. What are tints? Tints, when we add white to a pure color, we get tint of that color. So when we add white, so the white is on the top, so tints are on the top plane, and between the center and towards the boundary, all the colors that lie there are the tints. Okay. And the tones are all the colors that lie inside the volume, inside the hex cone, are all the tones. So pure colors lie on the top plane and on the boundary. So H is 0 to 360, S is 1, V is 1 for pure colors. Gray, the central line from black to white. 0 to 360 is H, S is 0 because at the center S is 0, V varies from center to boundary, that is V varies from bottom to top, 0 to 1. Okay. So for shades, as they are the outer surface of the hex cone, they lie on the boundary and outer surface of the hex cone. 0 to 360, S is 1 because it is the boundary, and V value varies from 0 to 1. Tints, S is 0 to 1, V is equal to 1 because V is equal to 1 is the top plane of the hexagonal cone. And tones are all the colors that lie inside the volume of the hex cone. So we can perform conversions between RGB and HSV and vice versa. Sometimes you might require to convert from one color model to the other color model. When you do that, it might also happen that the color that is possible in one color model may not be possible in the other color model. I can give you a simple example. When you say you can open Photoshop, if you are interested in Photoshop, you can just open an image in one color model and try to convert that into another color model. You might see a kind of alert symbol, a triangle and an exclamation inside, that indicates that when you are trying to convert the image from one color model to the other color model, there is a possibility that some of the colors in the original color model may not be possible in the target color model. So there can be some out of gamut colors. If you say okay, what it will do is it will find the closest approximation to that color and it will replace that with that color model. Okay. So you can do simple conversions between HSV and RGB and vice versa. As you can see, how do we do a conversion is, if you say RGB color cube, if you see it is a cubic, it is a cube, and the shape or the volume for HSV color model is hexagon. When you see it from top, it looks like a hexagon for the HSV color model. When you see the RGB color cube, exactly if your viewing direction is aligned with the diagonal of the cube, that is the gray line of the cube connecting black and white, you will see 3 faces of the cube. So, if you forget the if you just ignore the lines inside, so it is also a hexagon. The RGB color cube also is a hexagon, as you can see when the viewing direction is aligned with the diagonal connecting black and white. This is also a hexagon, that is also a hexagon. You can easily compare these 2 hexagons and you can do this. And the last color model, which is HLS color model, which is simply an extension of HSV color model, where we are extending the hex cone on the upper side, that is we are inverting the hex cone and putting another hex cone on top. So, it is called a double hex cone. So, what is a double hex cone? So, we are simply extending this color model such that the 2 hex cones are one inverted above the other, that is one above the other, and the central line connecting the black and white vertices is the gray line again. But the difference between the HSV and HLS color models is that the central, that is the central position, central plane of this HLS color model is where the pure colors lie. Okay. On the top it is white, on the bottom it is black, and any color is represented with 3 values H, L and S. H is hue as usual, S is saturation. Instead of V there, we are using another variable L only to separate the 2. For pure colors, L is actually 0.5. So, L is the vertex, L is the axis connecting the vertices black and white. So, L is 0.5 for pure colors, H is 0 to 360, again the same angle, and saturation is 1. So, S is 1, L is 0.5, H is 0 to 360 for pure colors, and gray is the central line connecting all colors that lie on the central line or the axis connecting the black and white vertices. So, L is equal to 0 to 1, S is 0 and H is 0 to 360. Shades, when we add black pigment to a pure color, we get shades of that. Now, shades lie in the bottom half of the HLS color model on the boundary. Okay. Tints lie on the upper half of the double hex cone and on the boundary, and tones lie, the tones are nothing but all the colors that lie on the entire inside of the double hex cone. Okay. So, with that we come to the end of these color models discussion, an important discussion, and graphics without color models is like it does not sound well, and you need to also know that there are a lot of applications of color models. And I said one important thing, this color gamut, why do we have these many color models, is that the color gamut is different for different color models. Not all colors in the world are possible in one color model. Okay. So, RGB, CMY, YIQ, HSV and HLS are the color models that we have learned in today's module, in today's session. So, with this we come to the end of the color models discussion. Thank you.